Bismillahirrahmanirrahim. Assalamu alaikum class. This is your teacher Umar Shami for the MSc course of Advanced Power Electronics semester Spring 2020. Last time we started with chapter number 6, DC to DC converters, and today in this video lecture I would like to complete and finish chapter number 6 inshallah. Okay, so let us start with our lecture. We have done article number 6.1, and today we will start with article number 6.2. Article number 6.2 title is step down choppers. Step down choppers are also the step down DC-DC converter. However, in this article we are going to study universal step down DC-DC converters. Okay. So normal buck mode or buck type of converter that you might have studied will only operate in the first quadrant. In article 6.2 we are going to analyze universal step down converters which will operate in all four modes. So what do I mean by four modes or four quadrants which will work in all four quadrants? What do we mean by when we say that we have a universal converter which will operate in all four modes or four quadrants? So let us have a look. We will look at the voltage current characteristics of a power supply which can operate in all the four quadrants. So here in this we have current on the x-axis and voltage on the y-axis. A power supply working in the first quadrant will have the following properties. That is, a power supply in the first quadrant will act as a power source, voltage will be positive, current will be positive, and power will be delivered from the supply to the load. So this is a circuit or a power electronic circuit which is working in the first quadrant, and it behaves as a positive power source or the positive power supply. Right. In what is happening in the second quadrant? In the second quadrant, the function of the power electronic circuit will be to sink power or to absorb power. To sink power or to absorb power, where the voltage will be positive. The voltage will, no doubt, it will be positive, but the current will now flow from the load to the source. In quadrant number 1, the voltage was positive. In quadrant number 2, voltage is positive. In quadrant number 1, the current was positive. That is, the direction of current was flowing from the power supply to the load. This is what is happening in the first quadrant. But in the second quadrant, the power source remains the same. However, in the second quadrant, the current changes its direction and flows from the load into the source. We will discuss about this load after we finish the four quadrants. Now, what is happening in the third quadrant? That in the third quadrant The circuit acts as a minus power source, that is a negative power supply. That is, the voltage is now reversed and current is also reversed. So voltage is reversed, the current is reversed. So this time current is again flowing from the source to the load. So it is providing, the source is providing power to the load, and it is like a battery reversed in direction. It is like a battery that is reversed in direction. And in the fourth quadrant, what we have is we have a negative voltage but a positive current. That is, the current has reversed, voltage did not reverse. So here current now flows from the load to the source, whereas voltage remains negative. So in this we can say that it is again sinking or absorbing power, that is, load is providing current to the source. Now we need all of these four operations. We need operation in all four quadrants. We will see an example. We need a power supply that can provide positive voltage and provide current. We need a power supply that can provide positive voltage and absorb current. We need a power supply with reverse polarity, that is negative polarity, and it should also provide current with negative polarity. And we also need a power supply which will provide negative voltage but current will flow into the power supply. This is achieved using a universal type step down chopper, and this is what we will study. Now, why do we need operation in all the four modes? We will answer this question by looking at the diagram in the circuit shown above. It is a very good example that explains the necessity, or why it is essential to have, why it is important to have a universal DC-DC power supply. The example shows a DC motor where the R represents, where the example shows a load which represents a DC motor, R, L and E. R represents the resistance of the copper winding, L represents the inductance, whereas E represents the back EMF produced by the produced in the armature of the motor, DC motor. And we need, to make current flow, we have to provide a voltage that is larger than E, the back EMF. So the DC motor, when we provide voltage, when we provide a positive voltage, we may assume that the DC motor rotates in clockwise direction. And if we want to reverse the direction of the motor, then we will have to reverse the voltage. So DC motor running in first quadrant may produce a rotation in clockwise direction, and in the third quadrant, where a negative voltage has been supplied, the direction of the motor rotation might be counterclockwise direction. So we need a universal power supply through which we can get speed reversal. Now in the second slide, we will look at the mechanical properties of motors in four quadrants. That is, a motor we have in this diagram, the red line shows the motor motion and the black line shows the torque. When the motor and the torque are both in the same direction, then the motor is working in quadrant number 1. However, if we want to bring the motor to a stop, then we will have to supply torque in the opposite direction. However, due to momentum, the direction of speed will remain the same. Therefore, at this time, the mechanical motion is working in the second quadrant. In the third quadrant, again the motor and the torque are flowing in counterclockwise direction. And if we want to reduce the speed or bring the mechanical motion or rotation to zero, we can look at the fourth quadrant, where the torque has now is acting in the opposite direction. So this is a graph of mechanical rotation in four quadrants. For example, if we want to move the motor in clockwise direction, we can supply clockwise. If we want to move the motor in clockwise direction, then we can supply positive current, and the motor starts to rotate. But if we want to bring the motor to a stop, we don't want the motor to change its direction, we want the motor to come to a stop, then we have three options. First option is that we use mechanical brakes. We supply power, but at the same time we apply mechanical brake. This will cause wear and tear, and it will increase the price, it will increase of the system, it will increase the volume of the system, the space required of the system. Plus the system will be inefficient, because at one time we are supplying power, and at the same time we are applying the brakes. Second technique is that we open circuit the power supply. We keep the machine floating, that is, we disconnect. That is, so we are disengaged ourselves. We don't know about any electrical properties of the machine. This is also not wise. Third technique is that we make current flow in the opposite direction. We purposely make current to flow from the back EMF into the power supply. We make the back EMF as the power supply source, and we make the source equivalent to a load, and we allow current to flow from the back EMF into the source. So therefore the energy is being transferred back to the source. And this will bring the motor to a rest. Now if we want to reverse the speed, then we can reverse the voltage power supply. And if we want to reduce the speed while rotating in the opposite direction, we can now work in the fourth quadrant, where the motor will supply current back to the source. So we need a converter which has the capability of transferring current from source to load, and transferring current from load to source, and at the same time it should have the capability of reversing its voltage. It will always have two terminals, but these two terminals will not now be permanent. Like in the case of a DC battery, the terminals are permanent. One is always positive, one is always negative. In the universal DC power supply, the terminals, they are not permanently defined, and the polarity will change as per required. So we will look at the universal converter, and especially in this book we will look at the converter working, in how the converter works in all four quadrants. Okay जी, अब हमने अगली स्लाइड में in our next slide, what we will do is we will now combine the properties of motion and torque versus our properties of voltage and current. That is, we will now combine these mechanical properties versus the voltage and current properties, so as to look and understand that how the chopper and how the motor will interact for all four quadrants. So now we are going to combine for all the four quadrants. So now we are going to combine the voltage and current characteristics and the motion and torque characteristics for our DC motor application. So in the next slide, here we have the chopper, and here is the graph between torque on the y-axis and speed on the x-axis. So in the first quadrant, we have motor running as usual. We have the motor operation where the input supplied voltage is larger than the back EMF. The supply voltage is larger than the back EMF. As a result, current flows from the chopper into the motor. Now, this is called forward motoring. That is, motor is rotating in clockwise direction. Okay? And then in the second quadrant, we have forward braking. This can also be called as clockwise braking. That is, the motor is rotating in clockwise, but at the same time we are also reducing the speed. As a result, the energy must flow from the motor into the source, from the motor into the chopper. And this is what we are having in the second quadrant, where the back EMF is now greater than the voltage, source voltage. The back EMF voltage is now larger as compared to the source voltage. As a result, current flows from the back EMF into the source. Hence, we are returning the power. We are returning the energy from the motor to the source. And when we return the energy, the rotor of the motor will come to a stop. Therefore, it is called forward braking, or it can also be called as clockwise braking. Okay, now let us look at the third quadrant, where the title of the third quadrant is reverse motoring. That is, the rotor of the motor is now rotating in the counterclockwise direction. Remember that in the first quadrant we had forward motoring, where the motor was rotating in the clockwise direction, and now in the third quadrant we have the reverse motoring. That is, motor is rotating in the counterclockwise direction, which is only possible if we apply the reverse polarity. If we apply a reverse polarity as compared to, or as compared to as voltage applied in the first quadrant. So we can see that in the third quadrant, in the reverse motoring, we have reversed the polarity of the source. We have reversed the polarity. In the first quadrant we have plus minus, and in the third quadrant we have minus plus. However, in this case, current flows from the power supply to the back EMF, to the motor, and this current IA, which is flowing, this current, it looks as if this current is flowing from the motor to the load, but if we must understand that our conventional current will flow in this direction, so therefore current is now being fed to the motor. The motor is acting like a normal motor. Now, if we want to reduce the motor speed, then we have to make, if we want to reduce the motor speed, then we have to make the voltage of the source less than the back EMF. You have to make back EMF. Okay? So in the fourth quadrant, what we are doing is we are applying reverse braking. That is, motor is flowing in the counterclockwise direction, but we want to reduce the speed. This will be done when we make the back EMF voltage larger than the voltage of the power supply. And as a result, what will happen? Current will flow from the motor into the source like this. What have we done? We have done the same as we did in the second quadrant, that we have returned the energy from the motor into the source. Now, if we stop here for a while and we think that sometimes we are supplying power, we are supplying energy from source to motor, and sometimes we are supplying energy, returning energy from load to the source. This cannot be achieved while working only in the first quadrant, and motor running in clockwise direction and counterclockwise direction. This also cannot be achieved while working only in the first quadrant. So we need a universal DC-DC chopper or a DC-DC converter which will give us the freedom of stopping the motor, controlling the motor, reversing the speed of the motor. Hence, this is the requirement, and after this slide we will come to the circuit which will implement the universal DC-DC converter, which operates in all the 4 modes. And before we come to the actual circuits, we will also look at the important formulas. So in the next slide we will just have a quick view on the formulas, and then we will come to the actual circuits. So the average output voltage V out DC depends linearly on the duty ratio of the chopper switches, and generally can be controlled in the range of minus V in to plus V in. This is the input. This is the same input voltage, so output voltage ranges from minus V in to plus V in. As a result, consequently the magnitude control ratio M of a chopper can be written as or taken as M is equal to V out over V in. This is equation 6.1. So if we look at the load, then the applying Kirchhoff's voltage law, we get that the V out is equal to back EMF plus voltage across resistance plus voltage across inductance equal to V out. And this is since equation number 6.2 is a differential equation, we can find current, and we will have the current as shown in equation number 6.3. Now this equation 6.3 is very interesting. Let us understand what equation 6.3 is saying. Equation 6.3 is telling us the general wave shape. It tells us what wave shape we should expect just by viewing equation 6.3. In equation 6.3, there is V out minus I minus back EMF divided by R, which is a constant number, plus back EMF minus V out R, again a constant term, plus I out at previous time at time t naught, plus into an exponential function. Now this is the interesting part, that we should expect that the output current will be a constant term being added with an exponential function. Constant term being added with an exponential function. This is the constant term, and the initial value of current and the exponential function. So we will see in later slides that yes, actually this waveform, that this equation 6.3 can be seen as per visualization, that we will see a constant term with an overriding exponential term. We will see this in the later slide, and this is quite visible from just viewing equation 6.3. After this we have the average output DC current. The average output DC current can be found by equation 6.4, where equation 6.4 says that output DC current, average DC current, is equal to the magnitude control ratio M into the input voltage, average input voltage, minus the back EMF divided by R. Now we will look at the article 6.2.1, the first quadrant chopper. This is the DC-DC step-down converter working in the first quadrant. Circuit diagram consists of input voltage, switch S, freewheeling diode D, and the load. The load is usual DC motor. This small diagram shows that this converter only works in the first quadrant. On the x-axis we have output current, on the y-axis we have output voltage, and this waveform shows that this converter will only work in the first quadrant. So now let us look at the voltage equations, and as written in our textbook, the first quadrant chopper can only produce positive DC output voltage and current. The average power always flows from source to the load. The circuit diagram of the chopper shown in figure 6.7 is identical to that of the static DC switch in figure 6.1. A switching variable X, that is when switch S is open and when it is short circuit, that is a variable, can be assigned to fully controlled switch S, and the output voltage of the chopper can be expressed as the Vout is equal to X switching function into input voltage, equation 6.5. So this is the same as the modulation index. When switch S is short circuit, then all input voltage is available at the output voltage. When switch S is open, then output voltage is 0. Right. So the DC output voltage is equal to the T on divided by T on plus T off into input voltage, which is expressed as duty cycle multiplied by input voltage, equation 6.6. And figure 6.9 shows us two modulations, M is equal to 0.5, M is equal to 7.5. The input voltage, the output voltage, and the output current are shown in figure 6.9. For two modulation indexes, M is equal to 5.5, M is equal to 0.5, and when M is equal to 0.75. So let us look over here, that this is our peak voltage equal to input voltage, and for the time when M is equal to 0.5, we have 50% on time and 50% off time. Hence the output voltage will be the average, that is just 50% of input voltage. Now it is very interesting to see that we have this triangular waveform. In fact, if we magnify, it is not triangular, it is exponential function, just as we saw in the previous current equation. And this current equation, as we saw in the equation, this current is riding a constant value. So here is the current being shown. This is the current that we saw in the mathematical expression, and here is the graphical expression, that the current has some initial value and it follows an exponential function. And as we increase the modulation to 0.75, the output voltage will increase, the average output voltage will increase, and the DC output current will also increase. This can be seen over here, that as M increases, the output voltage also increases and the output current is also increasing. Now in figure 6.10, we have just magnified one cycle of the current, that we have magnified one cycle of the current. And it is important to note over here that although the current expression, the mathematical equation of the current as seen in equation 6.3, that there is an exponential function, but the solution of exponential function becomes a very complex, time taking. So what authors have worked out is that we make a linear function, that is, we don't take exponential, we just consider it to be a straight line, and this will solve a lot of problems. Although we will not get the correct answers, but the approximate will be very close to the correct answers. And at the same time, what is the advantage? That we have saved time, calculation time. So although the mathematical equation has exponential function, but by using graphical functions we take a straight line instead of the exponential, just to make our calculation simple, just to save time. And whereas the answer of the straight line will be very close to the answer of the exponential. And to solve for this, the time saving, that we get an output current equal to delta I out divided by 2 under root 3. This is the advantage of applying graphical function to solve instead of the exponential function. Then in remaining we have the derivation, from equation 6.10 to equation 6.13. We have all the mathematical calculations. My students, they can study and they can ask me if the calculations are, the mathematical expressions are very straightforward, very simple to follow, and at the end we reach to equation 6.18. Okay, so yes, right. So now we will come to the next slide. The next slide is the new article. Article is 6.2.2. It is the operation of our universal DC-DC converter in the second quadrant. And in this quadrant, or in this mode, we will now understand how current flows from the motor to the source. How current, and if we can just go back to a few slides, we will see what we are going to do. So we are going to now study the converter in the second quadrant, where the function will be to absorb power from the load. The voltage will be positive, but now the current is negative. That is, now the current will flow in the opposite direction from the load to the source, and the power will be sourced from load to the power supply. And what now, this is what we want to achieve, that we will apply forward braking. Here current is flowing from the load to the source, and this is only possible when the back EMF is made larger than the source voltage. And so we have to fulfill this condition using our converter, and this will make it very interesting. So let us come to article 6.2.2. And this is a circuit, article 6.2.2, second quadrant chopper. There is, first of all, there is no such thing as an independent second quadrant chopper. There is a complete chopper which can operate either in first mode or in second mode. There is no separate circuit that this circuit can only, for example, this circuit is useless because it can only supply current from the load to the source. So to allow current to flow from source to load, we need the first quadrant chopper. Okay? So this circuit, it is a sub circuit of a main circuit, and that circuit we will see at the very end. Figure 6.12 shows the second quadrant chopper, where we have the input voltage, the reverse connected diode D, the switch S, current in the switch S is IS, and the output load voltage, our load, we will assume a DC motor with RLE, and E represents the back EMF. This second quadrant chopper will work in the second quadrant where the voltage is positive but the current is negative. So how do we make current flow from, how do we make the current flow from the load into the source? This has to be done so that we can bring the motor to a stop. We can apply braking, but the braking will decrease the efficiency. So the alternate technique is that we remove the energy in the inductor, we remove the energy in the motor, we return the energy from the motor to the load. That is, we reverse the direction of current. And on top of that, there is also a reverse connected diode. So we have to make current flow from the load into the source. But the question is, how do we make current flow from, how do we make current flow from E to VI? How do we do this? We will do this by, there is only one technique, that is, we will achieve this when V in is smaller than back EMF. This is the only technique to make current flow from the load to the source. That is, we make the voltage appearing across the load larger, uh, we make the load appearing across the larger than the source voltage. So just as a correction, that let us say that this, as a correction, this is point A and this is point B. So please note this correction, that current will flow from the load to the source when input voltage is smaller than V A B. This is an important relation. Only under this condition, current will flow from the load to the source. This is very important. When we meet this condition, only then current will flow from the load to the source. And this is what we are going to do. And this is, in fact, this is why we see the switch S. Switch S will make voltage VAB larger than VI. How will it be larger? Let us remove the red marker. Now here we see the back EMF, inductance, resistance R, and switch S, and a reverse connected diode. If we look closer, this is the exact circuit of a DC-DC boost converter. This is the diagram of the DC-DC boost converter. Here is the diagram of your normal DC-DC boost converter. It has only one switch, on and off. When we turn on the switch, current flows through the inductor, and this current charges the inductor, and as a result, this becomes positive and negative. And when we open the switch, the inductor voltage reverses in polarity, and we get output voltage which is larger. This is the exact concept that is being applied in figure 6.12 second quadrant chopper. Here is the voltage source. This is the inductor. The resistance R is very small, and here we see the switch. When we short circuit, the switch, let us see how figure 6.12 works as a DC boost converter. So we say that the author has written in state 1, switch S shorts the load and the load EMF. E supplies the resulting circuit, which includes the load inductance L. That is, when in state 1, this is state 1 when the switch is short circuit. If we look in the second quadrant, when it is state 1, then at that time this switch is short circuit. As a result, the back EMF charges the inductor, and this is positive and this is negative. Okay? So this is what is happening in the first when switch S is short circuit. After this, in state 0, energy stored in this inductance maintains the current, which is now forced to flow through the diode D into the supply source. What is happening? Yes, what is happening now? The switch is open. This is now open in state number 0. It is open like this. It is open now, but the inductor has current. So what the inductor will do is the inductor will reverse its polarity, and it will now force the current to flow into the it will flow force current to flow, it will now force current to flow into the power supply. And V, this is this is node A, this is node B. V A B is equal to back EMF plus voltage of inductor L. Now here we see that VAB is now larger than VI. As a result, current flows from the source of current flows from the load into the source because we have met this condition. So by the help of switch S and by the help of diode D, we are transporting current or transferring energy from the load into the source. The current, there's only one mechanism by which current can flow from the load to the source, that is we make the voltage VAB larger than the source voltage, and when we achieve this, current flows in the opposite direction as indicated by diode D. And next we have equation number 6.20, which indicates output voltage is 1 minus x into Vi. This is your normal DC-DC boost converter output voltage equation, and equation 6.21 is your average output voltage formula. So now, after studying these equations and the mechanism of how current is transferred, now let us look at the voltage and current waveforms of second quadrant chopper. We will now come to the second slide. Next slide. That our second quadrant chopper, again, figure 6.12, and here are the voltage and current waveforms. We see the input voltage, output voltage, the back EMF, and the output current. So we see for two example where modulation index M is equal to 0.5 and when M is equal to 0.25. Remember that the current that in the second quadrant the voltage will be positive but the current will be negative. Okay? So therefore in this graph we see the input voltage and we see the output voltage all positive, but now since current flows in the opposite direction, therefore we see a negative current which is less than 0. We see a negative current flowing in the opposite direction. First for M is equal to 0.5 and for M is equal to 0.25. So these are the waveforms. So these are the waveform for the second quadrant chopper. Now after studying the second quadrant chopper and first quadrant chopper independently, now we are going to combine the first and second quadrant chopper and let us see what we get. So we should expect a DC converter which can allow current to flow in both directions, but voltage reversal is not possible. This is what the first and second quadrant chopper can achieve. That current can be reversed, but voltage cannot be reversed. So we are just going to merge the first quadrant chopper and second quadrant chopper to one. We are going to combine them together. So here we see in figure number 6.15 the first and second quadrant chopper. It consists of one power supply, It consists of two switches, S1, S2. It consists of two diodes, D1, D2, and our load. And these quadrant shows this part of the diagram shows that such converter will be able to work in the first quadrant and in the second quadrant. In the first quadrant, the voltage is positive and the current is positive. In the second quadrant, the voltage is positive but the current is negative. So now let us identify out of these components which component make the first quadrant chopper and which quadrant make the second quadrant chopper. The input voltage, if you look closer, that S1, D1 and the load. The input voltage S1, D1 and the load, they make the first quadrant chopper. They make the first quadrant chopper. S1, D1 and the load, they make the first quadrant chopper. And S2, D2 and VI, they make the second quadrant chopper. S2, D2 and VI, they make we can identify them as the second quadrant chopper. Now what is this first and second quadrant chopper capable of? This is what it is capable of. The waveforms, where the voltage, output voltage, is a function of magnitude of the modulation index, but we can achieve positive current and negative current. We cannot achieve negative voltage, but we can achieve positive current and negative current. What is positive current? Positive current means when current flows from the source to the load. What is negative current? Negative current means when current flows from the source. Please note, when negative current means when the current flows from the load into the source. So here we see positive current. What is positive current? This is positive current starting from here into the load. This is positive current. And what is this negative current? What is this negative current? Negative current means that current after being boosted by S2, it will flow into the source voltage. Negative current. It is a boost operation. So such converter can rotate the motor only in one direction, but they can transfer energy from source to motor or motor to source. This is the advantage of such converter. Motor cannot change its direction of rotation. If the motor is rotating in clockwise direction, then such converter will only keep the motor running in clockwise direction. But when we want to stop the motor, the energy will be returned from the load, from the motor to the source. Now, if we want to reverse the voltage, what should we do? We should use the all four quadrant DC-DC. I will not discuss operation of the chopper in third quadrant and fourth quadrant alone because they are repetitions of first and second quadrant operation with current reversal. So the explanation of a third and fourth quadrant chopper is exactly the same, just like the first operation of first and second quadrant chopper. So I am now going to combine all the four quadrants and see what we get. So in this diagram 6.20, we have the four-quadrant chopper where current can be applied um, where voltage, first of all, voltage can be positive or negative. This is all four quadrant, and current can flow either positive or negative. The voltage is the voltage can vary from positive VI to minus VI, and current can be positive and negative. Positive and negative current means that current can flow into the load or out of the load. The advantage of such converter is that we can transfer power from source to the load while rotation can be changed clockwise or anti-clockwise. And also we can transfer energy back from the load into the source. This is the four-quadrant chopper. Okay. So uh, we will after this we will come to our next article. This is the article 6.3, which is called the step up chopper. Step up chopper is our normal DC-DC boost converter. DC-DC boost converter operates to enhance, is used to increase the output voltage beyond the input voltage. And this is achieved by using one switch S. That is, let us look at the operation of the DC-DC converter, boost converter, is that this switch, it will either be on or off. When the switch is turned on, that is, it is a short circuit. At that time, current will flow into this switch. It will short circuit the inductor, and during this time the current will charge the inductor and voltage will build up across the inductor like this. Right now we must not forget that current in the inductor cannot change instantaneously, but the voltage polarity of the inductor can change instantaneously. Voltage of the inductor can change any instantly as per required, but current in the inductor cannot change instantaneously. So in this chopper, when switch S is closed, the chopper charges the inductor, and then with the current flowing, we turn off the switch. When we turn off the switch, now what will happen is that the switch is now open, but there is a current in the inductor. Therefore, the inductor will build up a reverse voltage, and this reverse voltage will be added with the input voltage so that the voltage appearing across the load is larger than the input voltage, and therefore we have an output voltage equal to V in bracket 1 plus T on over T off. So this is our equation 6.7 defines or guides that the output voltage will always be larger than the input voltage because we have 1 plus over here. So it is always 1 plus the ratio, the duty ratio, or T on over T off. Then we have equations. Um, then we have average equation 6.38 is also again the output voltage equal to 1 VI divided by 1 minus D. D is the duty ratio, and the average output voltage is defined in equation 6.39. Okay. So after this we come to the last article chapter, that is the device selection of choppers, and we have to select our devices so that they can carry required current and they can bear required information. So let's see in the book. कि book में क्या जो इक्वेशन है 6.41, that is the rated voltage of the device. It is given by V rated must be larger than 1 plus SV. और यहाँ पे जो SV है, SV represents the safety voltage. फिर जो करंट की रेटिंग आपने सिलेक्ट करनी है, जो करंट will be larger than 1 plus S1 into I out DC, or and then the specific duty ratio is given in equation 6.43, or and the diode rating is given in equation 6.45. Okay. So we have now, alhamdulillah, completed chapter number 6, and in my next lecture we will start chapter number 7. Thank you very much for your time. Thank you very much for your attention. अल्लाह ताला आप सबको अपनी खास रहमत में रखे, आप सबका ख्याल रखें, हम सबके लिए दुआ करें. थैंक यू वेरी मच. अस्सलाम वालेकुम.